way back from New Zealand as we speak. So today, Mike James, please come on officially. I'd like to introduce you as a VP with ISCO Industries, the largest distributor of polyethylene pipe. And I also say, Mike, you're the largest fabricator of polyethylene pipe in the United States as well.
Yeah, we have about 10 fabrication shops around North America where we fabricate structures and fittings, as well as all the pipe that we distribute and the fusion equipment to go with it.
How would people and why would people interact with you and your sales team, Mike? Just give us a for instance of your role in this whole process.
So we're obviously hyper focused on HDPE piping systems, and we provide a total piping solution when it comes to your project. If we can engage with the engineer early on in a project, we can add more value early on. So we can help you with the technical side of it, the specs, the design of it. We're not going to stamp things for you, but we'll help guide you on what's available today for that. And then we'll walk you through the whole production side of things and the supply side, as well as when you have to get it installed. We have lots of contractors we work with that we can refer. We can educate them as well. We can provide fusion training services. Our job is really to make sure that the right pipe gets designed, installed correctly all the way through the whole process. And you know, there's a place like Jackson, Mississippi. Peter, did you see the news today on that? 5 million gallons per day leaking. I hope they're on this call. We need them on here as well.
Well, Mike, I've tried to get a hold of Jackson and I've tried to contribute like I've done in Flint. I've been working in Flint for 5 years, Mike. We finally made some progress. They're now committing to polyethylene in Flint. We have 3 projects in ground already, and we just had a meeting last month with their engineering consultants, Mike. I'm hopeful that we can help in Jackson, but you know, the next move's up to them. All right, next slide, please, Alan. So this is how you get a hold of us. You may want to take a screenshot of this, and let's move on to the next slide and get this thing going. All right, so Alan, why don't you come on and tell us a little bit about the EPA and the durability and the reliability according to the data from the Water Research Foundation.
So the Water Research Foundation is an independent research arm as part of AWWA and studies all sorts of things within the water market. So they did do a large study, some significant research about what size and diameters and DR ratings HDPE has been involved and included in people's systems through construction all the way through operation. And we were looking for failure rates. We're looking for fatigue failures, if those were there, prevalence of use. And the end result of the report, I like it when it's boiled down to the basics, and that shows that large diameter HDPE is suitable pipe material for large diameter water transmission and main applications. Pretty basic. This is also a slightly older technology, or not technology, but publication. So the industry itself has evolved in resin development and all sorts of things since then. So we're just getting better and better and better, Pete.
Yeah, that's for sure. Next screen, please. So, you know, you may say, well, yeah, this stuff sounds good, but is it really reliable? Richard Kolosik, could you come on and tell us about, you know, one of the ways we like to distinguish ourselves, Richard, is compare ourselves to PVC because it's the other plastic pipe. You know, PVC is a good product. It's not as good as ours, but PVC, Richard, suffers from cyclic fatigue. So you hit it, it's like a pitcher's arm. You hit it, throw so many pitches, eventually the arm's going to wear down. Same thing with PVC, Richard. What's up with 10 million cycles? Was that at full pressure or was that just like at 40 PSI? Tell us about that test.
No, that was a test done by GTI through the Hydrostatic Stress Board of the Plastics Pipe Institute. And what had happened is we wanted to understand cyclic resistance of polyethylene. So we developed a process to actually cycle at 500 and 625 hertz, which was basically 1.5 times and 2 times the operating pressure of the design DR of the high density. After all of those cycles, we had 0 failures. There was something like 235 samples with fusions, with fittings and everything in there. Yes, it was all smaller diameter, but the scale was still there. But it was all completely done with 0 failure. So we had to stop the test because it was just getting really, really expensive. I think it was about a $250 cost per site or per sample. So it was a little spendy, but it really told us a lot. And with other products that were tested, there was failure. The rigidity versus ductility differences between the two really emphasized itself in this test. So gave us the confidence to put a multiplier, not a reducer for surge effects.
So Richard, a mid-sized 250,000 person city, how many cycles would they see in 100 years?
Oh, like 100 years? Probably what they would typically see is about 500,000 per. It's 54 cycles a day is what we averaged the utilities. We surveyed 435 utilities, and we had an average number of about 54 cycles per day on average. And it depends, if it was a tower system or it was a pumping system, that was reduced on a tower system type application. But that was about, you can do the math yourself for 100 years. So
2 million cycles.
Yeah, so we're not even going to touch it. We're not even going to touch
Yeah.
the resistance. So we're very confident that surge effects are not going to have an impact on your performance of your pipe long term.
So then in the United Kingdom, their version of the Water Research Foundation is UKWIR, and that little graphic in the lower right-hand corner talks about polyethylene's failure rate. And it's the small bar on the right-hand side, so the light blue. It failed at half the number of times that PVC and ductile did. And our failures tend to be our third-party damage and bad fusions. So that's why we spend a lot of time talking about training.
And that was pre 4710. So our slow
Right.
crack growth resistance has really improved. So I wouldn't expect to see a bar there at all anymore.
Next slide, please.
Thank you.
All right. So Alan, why don't you take over here for a couple of slides and talk about design that lead to the durability and reliability of the product.
Sure. So some of the design aids that we have available for you, Pete mentioned the engineer's package previously. AWWA has a water main or a M55 manual for all things high density polyethylene pipe. There's also standards, ASTM standards. A lot of those references are included within this engineering package that we've got through, but there's lots of guides for you to be able to utilize to help if you've never designed a high density polyethylene project previously, or if you have a whole lot of complicated installations, in which case you need to look at additional information for your installation. So some of the Bible of polyethylene pipe happens to be the Plastic Pipe Institute Handbook on Polyethylene Pipe. 16 chapters, covers everything you might want to know about polyethylene pipe, including the material properties, pipe and fittings, how those are manufactured, design of that underground system. We even get into above ground applications to be able to look at thermal properties and restraint and the strain or stress that may develop in the pipe wall at those restraint locations as that pipe suffers thermal expansion through heat during the day or changes in weather. Marine installation, slip lining, horizontal directional drill, pipe bursting, and all sorts of other things. So the Alliance itself maintains additional spreadsheets that can be made available to you. We want to know a little bit more about your project before we turn over a calculator to you. So definitely make sure that you send us a note and include us in the development of your polyethylene project as we go. One of the most interesting things that Pete and I have discovered over the past several years is historically trenchless technologies such as horizontal directional design or drill was one of the gateway drugs, so to speak, for polyethylene use at municipalities. So that's just a first introductory use if you've never been able to use polyethylene in your system before. But over the past couple of years, we've started to hear more from you in the audience there as to what your projects are, and OpenCut has become an overwhelming installation method for you. So we've put together a simple design window for you. So if your pipe is in between DR7 and DR21, has an approximate burial depth of 2 feet for no H20 loading, that's a box truck loading, or 3 feet for regular live loading condition on top of it, and then buried down to a max height cover of 25 feet. This is a approximated design window corresponding with the new M55's basic installation method. There are other installation methods as to which you look at an engineered method. M55 will help you walk through that, but we also have calculators, so that will be going deeper depths or thinner wall pipe as we move through that. So as you start to incorporate larger diameter pipe, remember the footprint on everything expands. So if we're looking at 48-inch pipe, we want to make sure that we've got the appropriate trench width, the appropriate trench stabilization for that trench as we're going through, which oftentimes is more important than the distance for the pipe itself, because we want to make sure that that trench is safe and supported for the workers getting in and doing the work of that nature. So some of the working pressures and surge, I'm glad Richard previously had mentioned exactly what recurring surge was calculated for in about 55 cycles a day. So your pressure pipe, DR11 200 psi pressure pipe, can see about 300 psi of pressure surge per day at 55 cycles, and the occasional surge then is twice that pressure class, and so that'll be for 5 or 6 cycles. One important thing about large pipe that's distinguished between distribution networks and smaller pipes is we're often trying to get fluid from one place to another, and that's a fairly defined path with longer spacing on our valves and control valves and other things. So we don't have as much shifting as we would in a potable distribution network as to where water might be going to be able to provide whoever wants to use it. So we're going to see sometimes less surges as you'll have a more stable environment. We worked with a municipality in New England area that had 190 psi pre-stressed concrete cylinder pipe. I said, hey, what's your pressure variation? They put a surge gauge on that sucker for a while, and basically it stayed 190 flat for a long time. So I wouldn't have any issue saying, hey, look, you're operating at 190 psi. You probably should consider a DR11 at 200 psi. Plus, you have all of these other conservative factors right on top of that for you. So get back to installation, some of the durability and reliability. Some questions about installation historically are different from HDPE versus more rigid materials such as ductile iron and PVC. Some are going to be gauged towards the lack of ease of use of this product, tapping and fusions. So to highlight some of the viscoelastic behavior of high-density polyethylene, it provides us that extra durability and ductility during installation. So our contractors actually can work with this pipe material sometimes way easier than they can with a much more rigid pipe as we go through that. Tapping is going to be similar to what you'd see with a PVC pipe, as to which we want to tap through a fitting that supports that pipe material as it goes through. And then fusions. Like everything, we need training. We need training and qualified trainers for butt fusion, for electrofusion, to be able to understand how to be able to perform that fusion safely and effectively. And Pete and Mike are going to come on and talk a little bit more about that too.
So Mike, you showed that video before the show actually started of those guys up in Canada fusing, over 100-inch diameter pipe. That's not the guy that was just trained on a McElroy 28 machine. Tell us about that process.
Yeah, no, those weren't. Those are some of our veteran fusion technicians that actually went to Austria and got trained and came back and performed on that job. But, talk about training. Last week was a good example. I was in Colorado last week, and we trained a lot of people last week that had never touched polyethylene pipe. Some had, some hadn't. We can walk people through the very basic training, small diameter, simple fusions, all the way up through the most complicated training there is. Even in ditch, I see a question from Scott Funk about how do we perform in ditch fusions and so forth. We have specialty equipment. We have technicians that can come in and help you, either teach you how to do it, or we can come in and perform that fusion as well. So we can help you certainly on all aspects of training, not just with butt fusion, but with electrofusion, sidewall fusion, socket fusion, the whole 9 yards.
Yeah, the industry understands what's necessary to be able to ensure a proper fusion and is happy to be able to give you that information. And Mike James is standing by his crew all throughout the country to be able to help you in any fashion that you've got. So we have had a couple of questions roll in. Again, this makes it much more applicable to you when you ask those questions, and continue to roll them in, especially when we start to show you we're moving from some of the pre-slides here of design and information to actual handling and manipulation of the pipe as we go through. So I'm sure you're going to start asking more of those questions, and keep it up. So repair becomes one of these things that we do need to talk about. High density polyethylene does not solve that cyclic fatigue, does not corrode. So quite a bit of the industry has said, hey, after you get this installed, we're really not going to be a long-term problem for you. But then there's also third-party utility damage and maybe some contractor error at the beginning or what have you through it. So the Municipal Advisory Board of the Plastic Pipe Institute is a group of municipal representatives that live and breathe the adoption of high-density polyethylene into their systems. And they've come up with quite a lot of different helpful resources here. I'm showing you the MAB Basic 04 manual for itself. And this is a laminated sheet that's tied into a field workbook that can be thrown in the back of the truck for the operator. And it goes through a series of decision matrix to show exactly what is available to that operator at all times of night. Of course, your water main failure doesn't happen at 9 a.m. on a Tuesday after you just finish your coffee. It happens Christmas Eve, Christmas morning, 2 a.m., some type of time in that manner. So a mechanical spool piece is one possibility to be able to put through this. They do have mechanical connectors and adapters that are very specific to high density polyethylene to come in at 2 a.m., be able to slap right on that pipe. You shut it down, shut the valves down, you cut the pipe out, and then we'll put that spool piece back in where we know we need a piece of high density polyethylene pipe that's either been gouged or further damaged that has to be removed, that we can't put a repair clamp around it. A flanged spool piece is another method to be able to remove larger sections of pipe in that manner. You can also do that with an electrofusion spool piece as well. So by the time that we get down to electrofusion, it's important to have definitely all the water shut off within that pipeline as we run through. No fluid control can come through that section. Some of these other pieces and spool pieces can be done at a later date as well. That's not an emergency. If you've got a repair clamp to be able to come through and slap on the side of that pipeline at 2 a.m., that same repair clamp that you're used to put on some of your other pipe material can be the same thing. This does translate straight up into larger diameter fixes and repairs as we go through. So I'll walk you through this project that we've got going on. We have a repair that's required on a larger diameter piece of high density polyethylene pipe. I'm unaware if that was required to be a third party damage, maybe a pipe gouge on the outside itself. But if you translate and start to look at the installation of the fitting from when it arrives at the job site, wrap around that location of the repair that we need to itself, and then we translate that out further. So we know larger pipe requires more force and potentially has larger pressures going on the inside. So this particular adapter also has the belt and suspenders approach that engineers like in order to be able to put more thrust restraint on either side of that fitting in order to be able to tighten those bolts up, secure that, and make sure that that fitting is not going to translate or move after it's been installed through this. So the industry has thought through quite a bit of this, does have those tools available to you, and they are robust in that manner. So go ahead, Pete.
So on that previous slide, Hymax, Alan, makes band clamps up to 2 meters in diameter, which is the same size as McElroy's Talon 2000. So we're making repair clamps to very large sizes.
Absolutely. So perception, we want to look through. Pete, if you want to stay on with me, we can talk about cost. And here's a good example of the City of Sunrise project that you can narrate through the video here. It looks like 12-inch, 44,000 linear feet of DR11 pipe that saved quite a bit of money.
Yeah, so this owner, so think suburb of Fort Lauderdale, was saved over $1 million on one small 12-inch pipe burst, Alan. By going polyethylene. It was originally bid as ductile iron, and that's what the utility was very comfortable with. Yet they were using polyethylene and gas all day. The contractor came in and said, hey, I can do it a lot less expensively and do it for a lot less than what you thought and save you a ton of money if we go polyethylene. So they did, saved a lot of money. Now, this is a story that we hear all the time. Unfortunately, I didn't have any good videos of this instance happening in large diameter, but I will work on that for next year.
Yep, for pipe bursting, they're getting well up into 36 inches, and the equipment is there for 54-inch. I know the industry itself is chomping at the bit to go for a 54 or 48-inch for pipe bursting itself. So much like all trenchless projects, once we start to see a more efficient and effective way to be able to install or rehabilitate pipe, we're going to start to see that reaped reward of cost savings, environmental savings, less social impact, in the whole 9 yards. So we're getting closer. We're 30 minutes in now, got good questions rolling, so make sure you keep it going. Some of the things that are important to talk about, and a full 10-year development in this industry itself. Some of the perception was harder, that you'd have to buy the equipment to be able to work with this pipe at all. ID matching was a conversation itself between different pipe sizes, and the surge pressures within a pipe from a higher velocity change, because of the viscoelastic behavior of high density polyethylene, are actually fairly attenuated with higher velocity changes. So we're not going to see those higher surge pressures through that system itself, and it definitely should be considered for a larger diameter. Yes, Pete.
So the PVC folks, Alan, love to talk about, oh, you got to match the ID, because as you all know on the call, we get our pressure rating by the thicker wall, we get greater pressure. So the PVC folks use this to your advantage. Could you just give me the top line, Alan? Say what you said again. But what I hear you say is that polyethylene, if we're going to jam more water into a smaller ID, our velocity is going to go up. But since we can handle that, that's not an issue. Am I understanding it correctly?
That's correct. Yes. And most distribution systems, the friction loss that comes through and really contributes quite a bit are the bends, fittings, and other things that go through a pipe network system, as to which the ID itself will just, if we have a constricted ID for HDPE, we'll have a higher velocity through that can be attenuated within the pipe itself. So it's your theoretical no connection between one very long pipe situation that we really want to look at friction loss in that idea of it, with no connections, no detriment to valves and other things. Mike,
thank you for explaining it. Mike.
Yeah, just I'll chime in. I mean, Kalasa can probably do this in Danish as well. I think when we go in and talk to engineers about HDPE piping systems compared to other materials, sometimes it gets over designed using our pipe. I mean, we can handle those surge pressures much better than other materials. I think that's one important thing. What's the working pressure? That's really what we want to know. What is your working pressure? You're going to have surge. We know that. We can handle that much better than other materials, but tell us what the working pressure is, tell us what the temperature is, and we can help you design around that. I think a lot of times we get over designed and therefore we get specced out of things. I think if we were to look at it differently, I think we would do better in that application. The other part too, I was with two engineers last week and they both had different information. And the question was, when you fuse HDPE together, is that a fully restrained system? One person thought, no, it wasn't. And one person thought, I think it is. We gave them the right answer. And yes, it is a fully restrained system. So we want to get clear on that as well.
So, Mike, I think it's worth exploring. I feel like we're on one of the podcasts right now, but I feel like it's worth exploring that argument that you just made about why polyethylene gets over-designed. You know what, Mike? It makes sense. When people don't understand it as well, they want to be safe, right?
Yeah. And I mean, you want to design it correctly and you want some safety factor in there for sure. But I think as we get into bigger pipes, for sure, we just haven't played in that space for a long time. There was people last week when I was talking to them that have just designed steel pipe their whole career, right? And
right.
That's all they know. So it was like a big eye opener to them last week when we started presenting information to them. So
yeah, well, good job. So Alan put on here, not for water. For many years, the transition, speaking of transitions, would be utility would use it for sewer because that was safe, but it's not for water, right? Well, nobody talks that way anymore. We have C901, we have C906. It's accepted by AWWA, NSF, ASTM. So we're very proud of that, but it's just part of the deal. It's the cost of getting into the game. And then, our competition loves to say, oh, you need training. Like, you don't really? So you're going to teach somebody in a trench. Okay, we're asking you to have somebody earn a card in steel, Alan. How long does it take to get you to become a welder in steel?
That's a great question, Pete. I don't know the direct answer, but one would assume it's certainly longer in that manner to be able to work with a flame and work with all sorts of other metal bonding as they go through that.
It's
An
a
open
year.
flame
It's
is
a year
significantly-
apprenticeship. And for us, we're asking for a day on small diameter. Mike told us that his crew went to learn how to use that Agra machine. They went to Europe. We're not asking for that kind of commitment, but if you're going to run polyethylene in your city, you're probably going to want to train one of your crews, and that could be a 1 to 3 day commitment depending on diameter.
Absolutely. I've done it before with City of Castleberry when I was there previously, and we do it with municipalities all day long. So we're going to look at connection and fittings now. Very good observation, Mr. James, about whether or not the bead and the fused pipe for high density polyethylene was in fact a fully restrained system. A very big difference when we show on the roadshow floor after we fuse a pipe up. I immediately challenge guys to try to hold the other section and pull it apart. If you were to do that with a 4-inch Bell and Spigot PVC pipe, you could probably pull it apart. So by the time that we insert that Bell and Spigot pipe, there's none of that tension forces that really stops that sucker from being pulled apart. The joint on high density polyethylene pipe material is all high density polyethylene all throughout the entire structure of that joint. So that is a fully restrained joint. Now, we can't have that all throughout the system. We do have to go and attach to other things. And that's when we have MJ adapters. We look at thrust blocks primarily in the locations as to which we are going to attach to Bell and Spigot systems, because we do not want to pull that Bell and Spigot out of that system. So we do have other adapters and things for you to be able to fuse onto your pipe, or use flange adapters, fuse on there as well, or mechanical fittings that give you that thrust restraint as we go through. Quite a bit of what Mike James and ISCO can do for you, as well as to fabricate some of these in their areas as well as necessary. So when we talk about durability and reliability of this product pipe material, again, we look toward the Water Research Foundation. They defined these as 16-inch and larger within that study, but as you can tell from what Mike and Pete are talking about, we're starting to get up into much larger pipe sizes. And here's just a little bit more information for you there.
Yeah, Alan, thanks. If I can jump in, when Peter and I started talking about big pipe a couple of years ago, 36-inch kind of used to be big pipe, but today we're using 48, 54, 63, 65-inch. I think that's an everyday occurrence, and not just an ISCO thing. I think it's all of our industry, right? So much more common to see those sizes and diameters. And then even larger than that today, when you got Matt Danish on the phone, they can make up to 3,500 millimeter pipe. And we see that globally as we go around the world. They're using bigger pipe around the world than we are today in North America.
So Matt, I just got a question on the issue of, well, if you go bigger and you're constrained on your wall thickness, by definition, you carry less pressure. What kind of pressures and what kind of wall thicknesses are you seeing on 80 and 100-inch?
On the 80 and 100-inch, we're looking at up to 80 PSI for pressure for like a SDR26 pipe. And really, it's also depending on the temperature of the application.
So what kind of deliveries are we, somebody wants to do a 4-mile long 80-inch DR26. What's the cycle time on design for something like that?
For a design on the project?
Well, for production.
Oh, for production. We could probably knock that out in a couple of months.
Okay, so 2 months. So design engineers out there, follow up with some questions if you want specifics. We've got the guy on this call right now. Alan, take it away.
Okay. So we looked at the lowest leakage rate and failure rate of all pipe material within this WRF report. Something that is always been inherent to HDPE and its self-restrained joints was our performance in earthquakes. So we do talk quite about that, but it's very specific in seismic regions. So most of the utilities that operate within a seismic region itself are going to understand what pipes are going to do what for their area itself. No corrosion does resist that rapid crack propagation, and essentially rapid crack propagation is an impingement or a failure within the pipe running across a fused joint. The advanced resin of the 4710s and above have all solved for that rapid crack propagation to stop that and restrain that from running across fused joints as we go through that. So here's some standards for us. So AWWA C906 goes from 4 to 665. An ASTM standard, as they say, gets up into that 3,500 millimeter pipe, which is a 10 plus feet pipe as we move through there. So in some installations, even though Matt had mentioned 80 PSI, some force main applications are still low pressure in the 30 PSI range. We'll show you one later that's a 54-inch horizontal directional drill that the actual operating condition was in the 35 PSI range. They did select a higher DR for 54-inch pipe just because they were putting it through horizontal directional drill in that manner. So be aware, sometimes the forces of installation are higher than the operating forces when we're using trenchless methods. And that's one of the things that's really pushed us to standardization of DR11 for potable water, even though it's 200 PSI operating pressure, and most water systems work between 55 and 70 PSI. And then DR17 for sewers, even though DR32.5 would work just fine as a sewer pipe itself in an engineered backfill. So Pete and Mike, if you guys want to come on and talk about some of the resin advances, I think this
Sure.
is where this really
Sorry,
takes
you
off.
caught me answering some questions. So yeah, the resin advances, Alan, are really quite wonderful. We've seen them all up and down the line. And if you've attended any of our webinars, you know that we've addressed the chlorine issue, we've addressed slow crack growth, and now we're very excited. And Mike James on the sales, in his sales operation, has seen the effects of this. And that is because we're now able to make thicker wall pipes. In other words, we're going from a 3-inch wall thickness, Mike, when we started talking about this. Now we've got Matt Danish making 6-inch wall thickness pipes. I mean, that's incredible. That's not happening every day, Mike, but certainly we're seeing 4- and 5-inch wall thicknesses.
I mean, look at that picture, right? I mean, that photo that we're showing there, Sean Gallagher's on the left-hand side. He's as tall as I am. He's 6'1", 6'2". That's a big pipe. That's going to Utah. That's the Steinecker project, I believe is what that is. And when I looked at that originally, I thought, oh, that looks like 3-inch thick pipe. He corrected me. He goes, no, it's almost like 5-inch thick pipe right there. Big diameter, heavy wall pipe. That we couldn't do 10 years ago here in North America. We're doing it today, which is awesome. So the change in the resin, the change in the extrusion capability, all of that today allows us to make bigger, heavier wall pipe.
Yeah, very exciting. So here just shows the resin capability. We're on the 4th generation resin now. And, you know, Mike, we kept the 4710 designation when we added the greater chlorine capability and the better slow crack growth resistance. What are some of the things that are on the horizon with resin that we might see in the next 10 years?
Yeah, well, you see how we've graduated today, right? We're going to continue to graduate. And as I look at what's going on around the world, PE 100 resin has been around for a decade or more. That's what they use in Europe and around the world. They're now using PE 125. So I know our next generation resin is coming right behind that as well, which will give us higher pressure ratings. And then with the low slag resins that are out there, we'll be able to produce even bigger sizes. So it's coming. It's better for the industry.
Tell us what you see here, Mike.
Well, this is Matt's pipe chart. Maybe Matt, you can jump on today and talk about this too. This is the pipe manufacturing chart that you guys have as well. And you guys go larger than what we show here, right?
Right. So this was an older chart that we've done back to go up to 71 inch. Now we're going up to 10.5 feet in diameter. So yeah, it adds on to this, and we can produce pipe in these SDRs. As you get to be the larger sizes, though, our SDR availability comes down. So once we get out to the very large size, we're only able to do that to an SDR 26 for the 80 PSI. And we also can do striping materials up to a 63 inch. And then after that, it's just black pipe.
Yeah, great stuff. Matt, the factory that you have, this isn't a picture of it here, but the factory that you have in South Carolina, right? I mean, you can even extrude long lengths of pipe right into the bay there. Is that correct?
Right. And depending on what the customer needs are, we can make it longer. If they can get longer trucks in, we can make it up to 53 on some truck beds. Will allow us to go up to 53-foot lengths. So all that can be prearranged, just as long as we have trucks that can handle longer lengths.
Yeah, good stuff. Hey, Matt, let's talk about some of the testing that you do at the factory, because I think if I'm an engineer designing maybe a project with HDPE for the first time, how do I know that you're making quality pipe at the factory?
So quality of the pipe starts from the beginning with raw materials, going through all the testing on the raw material to ensure that it meets all of the requirements, and then into the production of the pipe. We will monitor the pipe for all the different properties associated. And most important, what you're seeing here with these tensile samples is weld samples. So what we do is we offer the services to test weld samples for our installers to ensure that the setup on the machines, everything on the job site is good to go. So we'll do a sample welds. We'll bring those back in and pull tensile samples just to ensure that all the properties are being met and we're getting ductility with our weld samples. As you can see here is a weld sample that does not have good ductility. This was done with a different brand new machine that still needed to be calibrated. And so we were able to tell very quickly whether or not the welding machine is set up properly for all the procedures and all the parameters associated with the welding method. And so this is just a little diagram to the right is as you get to be thicker wall thickness, it changes the physics of the welding operation, meaning that when you look at of joining the two pieces together, the material in the center of the wall thickness has such a larger distance to travel. And that travel distance with time gives you the speed. Speed is not the friend for molten plastic. It likes to meander very slowly in a more laminar flow. When you start to increase that pressure of the weld, you get velocities that exceed the fusion pressure and time of under pressure. And so we really encourage people to look at their welding procedures and parameters to ensure that we have good welds. And then we also can do different types of tests. These are samples on the left are a constant tension load test where we can do tensile loads on the test to test for stress crack of the pipe. And then there's also the old method of doing weld test with the bend back test method. And then you have the recording for a joint to ensure that you have good joints and weldability in the large diameter pipes.
Yeah, so I think it's safe to say, Matt, if you're a new engineer or an engineer designing HDPE for the first time, there's lots of different test methods for the production, the resin at the pipe, producing the pipe, tensile impact tests. And then when you get it into the field, we can perform quality fusion tests in the field and qualify each operator, each fusion machine. We can help you design those. So if you reach out to us, we'll help you with your specifications. We really want to make sure that the pipe gets installed correctly all the way through the project. And we've got the tools to help you with that.
This part of the process always amazed me, Mike and Matt, because as a civil engineer, I was really focused on installation, making sure the project was managed, making sure we had what we needed to do, getting a good construction price. And then when I started to learn just every bit of testing that you on whole as an industry do to meet ASTM standards and the Hydrostatic Design Board, my eyes were just really opened up. It's amazing how many steps that material actually has to go through before it's even put on the job site. So that gave me yet even more support through that process of being able to specify HDPE. So
You're right. Alan, I would like to add too, I think it's while we're talking about testing and the importance of it too, I think it's something should be said about being pragmatic about like not overdoing it too, so you don't like boost your costs up. Like you don't want to have to do a fusion test perhaps every single day, right? You want to do it every so often, or maybe with every new operator. So I think if you just reach out and we have those conversations, we can help you build the right specifications for your project.
That's especially important in large pipe, Mike, is some of the heat up, cool down times that we might have limit us to maybe 5 productive joints a day. And if we only have 5 productive joints on a 48-inch pipe, if we choose to destructively test one of them, we're gutting the productivity by 80% there. So,
Yeah.
Well, Alan, you're so right. And speaking of handling, there are some very particular material handling types of equipment that we see, and we're thankful for McElroy for coming up with a lot of them. There's a low profile roller on the right-hand side. You probably want to use one of those on really heavy pipe, but on your smaller diameters, a lot of people just use bales of hay and, Mike, pieces of PVC, if you will.
Yeah, with small pipe, it's a lot easier. Certainly with big pipe, though, as you're handling bigger pipes, you want to make sure that you're loading the pipe correctly into the fusion machine and you have it lined up correctly for your fusion. McElroy's got some great equipment, as you see here, the track fusion machines, T900 and T1200, that will speed up the productivity of your job if you're pipelining down a right of way. Great tools.
Mike, what do those numbers 900 and 1200 mean?
Those are metric, but T900 basically will take you up to 36-inch diameter pipes, and a T1200 will take you up to 48-inch diameter.
Okay, so 1200 is 1.2 meters, 900 is 0.9 meters. Got it.
900, yeah, exactly.
Yeah, got it.
Yeah,
and here's the 1600, which is a 1.6 meter machine. One of the things that I noticed, Mike, that I don't really understand about how McElroy labels their machines, or when they get bigger, they go away from 4 jaws, they go back down to 2 jaws.
Well, they have a machine, a 2065, that is a 2-jaw machine, but they also have its big brother, this one here, the 1600, that actually has 4 jaws, which gives you that extra clamping force. Especially if we're getting the heavier wall pipe, you need that extra clamping force to make sure your fusions are done correctly.
Got it. Thanks for explaining that. Now, Mike, we had a question about 20 minutes ago about in-ditch fusion, particularly with larger diameter. Tell us a little bit about that.
Yeah, will do. Yeah, Scott, thanks for the question too on that as well. So, the machines that we just showed, most of those you can take them off of the carriage and get them down in the trench like you see here. So when you have to do a tie-in fusion, or maybe even a repair, or maybe you're taking 2 long strings and you have to put those together, here's a way you can do it. You can get down to 3 jaws. We even can get down to 2 jaws on some of our equipment that we manufacture, but you can actually take that down in the trench and locate your heater and your facer in there as well. So you can do in-ditch fusions. Now, the productivity is a little different. You're not going to do them as quickly or as fast, but when you need to do a fusion, which is what we recommend versus maybe a mechanical fitting or a flange, you can do it with these machines.
Hey, that's like on every big pipe job, Mike, as we get larger and larger in diameter, the logistics of being able to work with that pipe, manipulate it, and move it around just continue to have to be thought through by the construction project manager. And some concepts should be given at the design side to be able to see what is not suitable from an actual design project standpoint as well. So I always try to keep in mind the size of the equipment necessary when designing any project to make sure that we're not trying to shove 12 pounds of something in a 2-pound bag in that manner. So
yeah, and when you're trench boxing and things like that too, I mean, these things all come up, and if you just pull us in, we'll have those discussions, and maybe it changes the way you're going to construct your pipeline. A lot of people have a methodology that they are used to using with stick pipe, And maybe it has to change when you use longer lengths with HDPE and you're doing fusion. So we can help you with that. What you see on the screen here is the McElroy Talon, which is McElroy's largest machine. That's a 2-meter fusion machine that we have in our fleet as well. That's capable of welding up to 2 meter in diameter, I believe, down to 54-inch, I think is the smallest diameter. That's a track-driven machine that tracks over the pipeline. I think you'll see a couple pictures of it coming up as well. So those are available. This shows the facing mechanism in it as well, and shows you kind of how big the machine is. It also comes with a data logger type operation as well, so you can track all of the fusions, but it's more of a push button control machine versus the standard hydraulic units.
One of the things, Mike, that always amazed me about looking at McElroy's design of their machines and the industry on whole is just how almost idiot proof they make a lot of the steps of the actual machine, as to which it'll handle the cleaning, the scraping and facing the pipe to be able to get down to that virgin resin. And those who may be questioning the pipe material and how come it's so strong at the joint, essentially what we're doing is we're getting back to virgin high density polyethylene material, just like the way that we would in an extrusion facility. So if we get back to that virgin HDPE resin, your pipe manipulation and extrusion at butt fusion, electrofusion, sidewall fusion, any of those is going to be exactly the same when properly handled. And that's how it gets us right back to a joint that is as strong, if not stronger, than the pipe itself. And the industry's ability to think through those steps and ensure that we are successfully fusing at every spot. You guys have really done a good job to make sure that HDPE does exactly what we want it to do.
You want me to talk about this, Alan?
Yeah, please.
Okay. Yeah, great. So this is the Talon actually on site in Alaska. This is a hydroelectric penstock project that was done in a remote area in Alaska. It was actually a really, really great application for the Talon. I think the contractor saw that and brought it up to Alaska. So this is welding. Don't mind the color of the pipe. It's orange for a reason, but it could be black, it could be gray, it could be orange. Doesn't really matter what color it is. That is a polyethylene piping system that's running through remote areas of Alaska from a lake down to a penstock line. So the Talon in this application was fantastic. You can't really tell from that picture, but I mean, there's some pretty steep inclines that this was tracking over the pipe. They were able to put the pipe along the right of way, track over it, and do the fusions all across the project there.
We've got about 15 minutes left, everybody, and we're going to transition and shift into case studies. And before we do that, I want to talk a little bit about pipe failure. Now, when we get into larger diameter pipes, that consequence of that pipe failure dramatically increases. We can combine some of that analysis when we know the pain of failure for a larger 48-inch diameter pre-stressed concrete cylinder pipe with some statistical analysis of that pipe design itself and pipe installation. And I look to Water Research Foundation for quite a bit of information across all pipe types. They've got one on pre-stressed concrete cylinder pipe that shows specific generations of trying to install or manufacture as much of that pipe material as they can to push the boundaries of manufacture itself to where we have generations of certain types of pipes that are more likely and prone to failure. So when you're out there looking at all of your pipe material types, just a desktop view, and we're looking at a potential analysis as to what your prioritization of your capital improvement plan is, because you can't go out and fix every darn thing all at once, then this is one of those gut checks or desktop checks that you could go through and look at. So anybody that's lived through larger diameter or higher consequence pipe failure certainly didn't forget it. I've had to tell 25,000 people on Christmas morning that they couldn't drink their water. And let me tell you, I learned quite a bit from that effort. And that was really small diameter pipes, not certainly the consequence that we're going to go see. So I took this benefit now. We've got about 15 minutes left in the program, and we're going to talk a good good bit about very successful rehabilitation studies, move right into case studies, and show you some more good pictures on fittings and other things of that nature. But as we move into consequence of the failure, we start to look, these are the ones that are going to make that 10 o'clock news. These are the ones that they're going to be unhappy on Christmas morning that you couldn't put out good potable water in that manner. So these things are obviously going to connect and have high impact, and then hopefully drive your capital improvement program for you. So that way they'll be able to make sure that the commission felt just as bad through the process of not being able to provide that potable water or collect that gravity sewer, sanitary sewer force main through that, and realize that, hey, we've got this asset. It has this defined value, and let's go ahead and start to make sure we proactively repair that asset. So, Mike, this is one of yours up in ISCO, and I'll just outline the overall project itself. Southgate Sanitation District, 1.5 miles in a sewer tunnel. This is one of the prime questions I always ask, which is it a redundant line? So I've seen locations as to which there's not redundancy, or you have one pipe in and one pipe out from an island with 10,000 people. In this one, 100% of the district's capacity, or 12.4 million gallons a day. So to translate that up, 12.4 million gallons a day is a lot of people. Probably
A lot of poop.
that's a lot. You can't tell people to stop flushing their toilet, and about 100,000 people probably would make about 12.4 million gallons a day. Where else are you going to put it? Existing inspection of the tunnel itself showed lots of failure through it. Decommissioning a main of this nature can be hard to do unless it's planned for appropriately with outage periods. Again, can't tell 100,000 people they have to shut their toilet off. But slip lining this accomplished the project in $8 million when a new tunnel could have cost $30 million. So it's very successful. And go ahead and tell us about the fusion rate, which is always interesting, Mike.
Yeah, this was 48-inch heavy wall pipe. So I mean, the fusions take a while, right? So a couple hours for the complete process. And what was unique about this project is, as we're slip lining the pipe through this existing man-made tunnel that's been around for 50 years, they couldn't stop the flow. We had to put the pipe in there. There was a lot of unknowns about this project. The previous slide showed a directional drilling machine on there. We weren't drilling a hole, but they used the directional drilling machine you see in the bottom right-hand corner to actually pull the pipe through the tunnel. So it was fuse, let it cool, pull a section, fuse, let it cool, pull a section for 7,800 feet. It was about a month before we actually were able to get all of this pipe pulled through the tunnel. So you can imagine there were some sleepless nights, right? But it worked great. The buoyancy factor helped a bunch. We were able to do all the fusions inside of a tent and control that, debead everything, hooked it to this giant pull head, and completed the project and got it done. So it was an awesome job using a directional drilling machine for an unconventional purpose, but a great slipline project.
So the forces that would be experienced during construction of that need some hardened adapters and connectors. We obviously don't want that swivel to be able to break as it's rotating through there, and it allows that horizontal directional drill string as it comes through to be able to swivel and rotate through it. So the people that install this do understand it. Mike, I had no idea it was live flow condition, which is perfect. That's another.
Yeah, John Elway was happy. He could flush his toilet and everything worked just fine. It was in his neighborhood, but anyway, it was a great project. So
good. Here's another one, Pete, if you want to come on and talk to us about Fort Lauderdale. This is a large area as well, as to which we had pipe break and release of uncontrolled sewage within a very beautiful marina in that location.
Yeah, the Intercoastal Waterway took a hit with millions of tons of sewage, Alan. Polyethylene saved the day. So with some engineers and some smart folks in the polyethylene industry, the city of Fort Lauderdale decided to use polyethylene in a combination of 48-inch and 54-inch diameter horizontal directional drills throughout the area to replace the failing steel lines. Alan, go ahead to the next slide. And it was quite a project. It took a couple of years to get through it. 2 different contractors did the work. Murphy Pipelines, very prolific in social media, very educational. Find them if you can. Go ahead to the next slide. And I took a couple of videos of what it actually took to fuse up this pipe so that those of you that haven't seen large diameter fusion, you can see it. This is Mr. C working with, this is 48-inch, no, this is 54-inch polyethylene. On this fusion machine, he's got heavy equipment to move the pipe in and out of that fusion zone. And that, Mike, is one of those 2-jaw machines that you talk about that Murphy Pipeline rented from ISCO Industries. Or no, maybe they bought that one from you guys because I see their logo on it. This image shows what it's like. You know, you've got to keep that pipe at elevation because you don't want to create torque in the fusion zone. So these guys have a McElroy pipe stand, and they adjust its height based on what they need. So this takes 2 guys, another guy, a third guy is holding up the pipe string while they adjust the elevation of that roller. And that allows them to move that string once they've done a fusion so they can put in the next 50 feet. And if you haven't seen a large diameter fusion, this is what it looks like. So we just finished the heat soak. We're pulling out that heater plate and we have like 15 seconds to close it up. So the operator, Mr. C, is inspecting it. At the same time, he's closing the fusion zone and creating that double rollback bead. This is a fantastic example of what fusion looks like in large diameter. And then the last image we're going to look at is, you know, how do we move the next piece of pipe into that fusion zone? So here we've got the forks picking up the pipe on one end and pushing that pipe into the fusion zone of that large diameter fusion machine. And we'll just watch this through. And you can see him moving that pipe, and there's a fusion joint right there on the left-hand side of your screen. Quick examples, just thought it might be interesting. This video is, we showed it right at the beginning of the pre-show deck, but this is at 54-inch diameter, 40-foot deep, DR17, so about a 3-inch wall thickness, deepest, largest diameter horizontal directional drill that I know of in North America. And this saved a concrete line that was in the process of failing in Miami Beach. AECOM was the lead on this. ISCO advised the design build team. They saved the owner $3 million when compared to a microtunnel job. The design build team was given a year to do this job. They did it in 5 months, with actual construction being 5 weeks around the clock. So that was done 24/7. This is now in operation. And at a depth of 40 feet in the island of Miami Beach, it's all limestone. So they filled that borehole up with bentonite. They had 2 pipe strings they had to connect. So they connected the 2 pipe strings while they stopped the pull, fused it up, started it up again, and away they went. Alan.
Yep, this is that one pipe in, one pipe out scenario. And this is a low pressure force main for the only pipe out of Miami's South Beach to the regional treatment facility on Biscayne Bay. So the next ones we've got here are some fittings. And I believe Mike have some information for us on this, as well as getting to some of the irrigation successes that we've had. We've got about 7 minutes left. So these fittings that we're showing you obviously can be custom fabricated and built for what you've got. And they can just about make anything that you otherwise would like to have for your particular project. Go ahead, Mike.
Yeah, really, any elbows or T's or Y's or structures or any fittings you need, outlets like duckbill outlets or outlets for reducing valves or pressure outlets or anything like that. We can help you with that. Matt Danish, these are some of his fittings as well at Agru. So really, we have the capability of providing any of those fittings or structures like you see in these folks' pictures as well. So if you can draw it, we can build it. So yeah, if I can just touch base, I know we've got some folks on that have some interest on the irrigation side of things. And there's a lot of irrigation canals in the West that are being piped today, which we need. We have a lot of evaporation, a lot of water loss in the West. So I wanted to show a couple slides. This is a 48-inch project, I believe, that we did in Utah with the Kilpack boys there. Really common for us to do larger diameter, thinner wall pipes in the West using HDPE pipe. It's actually pretty simple. Those are pretty simple projects for us. The next picture, Matt Danish, maybe you can come on. We'll talk about Steinecker as well, because this is a large diameter irrigation canal. Matt, can you quickly chime in about this?
Yeah, so this project was very unique because we had such a small footprint to work in. The easement that the district was allowed was only, I think, 100 feet from fence to fence, and we had to stay within that boundary. So, as you know, if this is a canal, it's got a lot of these bends and turns in it. And one of the great things about the ISCO Talon welding machine is that we made these elbows where the Talon could walk right over them. So it drastically helped with the installation of this pipe system, because the elbows were laid down. The Talon was able to make the fuse and then walk right over the elbow and then continue that process down. So we welded all the pipe up on the roadway and then lowered it down into the trench. So that's one of the great things about HDPE. Whereas if you made this out of steel, they would actually had to weld that steel line into the trench where there's water and mud, and dewatering would be a very constant battle to uptake. Whereas here we're able to weld it right up on the roadway, stay out of the mud, and basically the pipe then just sat right down into the trench. The flexibility of the pipe just made it much easier to install. Even with some of the elbows, with some of the bends, it fit right nicely into the trench.
I'm so happy you guys show that, because keeping guys out of the trench and not having shoring in the trench to protect the guys is a huge productivity bonus. So thank you for showing that one.
Hey, Alan, real quick on that too. Just I want to hit on a really important topic here. This project that the engineer was on with us the other day, and he talked specifically about Steinecker Canal. They evaluated steel pipe, fiberglass pipe, and now with the extra size capability, HDPE pipe, they quickly eliminated steel pipe because of the cost. We went head to head against fiberglass. They let the contractor make the decision. We beat them hands down, I think, because of the installation method. We ship pipe all across the country, but that tells you how competitive we can be against steel pipe as well.
Apabsolutely. So here, just that same open cut land method with some animated GIFs, but proving the same point. And Mike, stay on and talk about seawater and OTEC here.
Yeah,
so how we're
just a quick example here. Even though this is not a municipal application, our pipes can be used and have been used in seawater air conditioning pipelines around the world, as well as OTEC pipelines. There's not that many OTEC projects, but they're being developed. It's all offshore. If you go to the next slide here, OTEC on the left, SWAC on the right. Don't need to get in the weeds on them, but they're both taking cold seawater, 40-degree seawater, bringing it up to the surface and either making power with it using the OTEC method, or taking it to a land-based heat exchanger and using it for air conditioning in large buildings and complexes. So great application for it as well. How are we doing on time?
We got only about 3 minutes left. So this is another ISCO project, a Clover Force Main 48-inch DR11, 3,300 meters. So it's quite a substantial amount of pipe is installed. As you can tell, we are trying to minimize the actual footprint of our construction altogether. And that really helps us to be able to make sure that we're being more cost effective in that manner.
In-ditch fusion right there. Yeah, I was just going to say that's a perfect application for an in-ditch fusion. So Scott, there's another answer to your question as well.
Absolutely. So we'll start to see saddles and other things being used for foul air or air release valves, which is very important in force mains as we go through. And they change the way that they do business in order to be able to increase that productivity level. So most contractors, once they start to look at how long of a run you could pull together successfully in advance, they're going to start to make sure that they are more productive in that manner. So additional information here that has fabricated fittings through it, just project after project after project of successful installations. This one's a marine application that had to have custom fittings as well, being able to put through and put forth. Again, more of that ocean water exchange where we're using the depth of the cold water in order to be able to change heat transfer to be able to push us through and air conditioning. Richard, you got about 30 seconds.
Yeah, just real quick, if you notice all those ballasts that are going to hold that pipe down, but you can calculate that weight for those ballasts and the distance apart. So when you fill that thing full of water, it'll drop down to the bottom of the ocean. If you need a repair or something happens to it, you can actually pump it full of air and that thing will come to the surface again. So it's kind of interesting to see all those ballast blocks on there and the pipe still floating. So it's really interesting technology there.
Alan, one
everybody come
final
on.
question, Alan, as it relates to those large diameters in the trenches. What kind of bedding are we using? What kind of backfill? Can we use native? What are the rules?
So that's a great question. So the bedding itself, we need to get a foundation that's free of rock, large rock. So on a very large pipe, we're talking bigger particle sizes. A 6 to 8 inch pipe would be a 3/4 inch. Anything above a 16 inch, we're looking at 1.5 inches. Richard was showing us the Bible on earthwork installation or pipe installation by Amster Howard. We basically can put a 57 stone, which is a standard stone, 3/4 inches around all of that pipe as we're going through, and we want to make sure that it's properly compacted as we go through that. But yes, the only time that we'd look for an engineered installation on large diameter pipe is when we're getting into that DR 26 or DR less than 21, and we can easily start to compact that backfill. The interaction of the pipe with the compacted backfill will do exactly what we need to be able to support the pipe. So let me get to our contact information since we're at 3:16. Richard, Mike, and Matt, if you guys want to come on and have any last words, this is it. We're
Dan,
right at
could
the
you
end
come
of it.
on and remind everybody how to get their PDH, please?
If you complete the form at the end of the program here, go ahead, Dan.
Yep, just the post-exit survey, just fill it out and we'll get that out to you as soon as we get the results.
All
Thank
right,
you.
Richard Colassa, thank you for working the bench. Dan, great job on the bench. Matt Danish, thank you for sponsoring the show and providing such excellent wisdom and knowledge. Mike James, always great to work with you. And Alan Ambler, thank you for putting together a great deck. And Dan, when will this talk be posted on YouTube?
It should be available sometime tonight.
Awesome. All right, with that, Alan will turn off Zoom and that poll will come up. You answer it. And within 2 weeks, give us 2 weeks, please, you will get your PDHs or your CEUs. Thank you all. I hope to see some of you tomorrow, same time, same station. We'll see you here on the webinar channel of the PE Alliance. Great job, everybody. And thank you all.